Hi, everybody. I hope your week has been going well so far. So this is going to be the first part of the Global Navigation Satellite System and Global Positioning Systems lecture. So last week I split up the lecture between Tuesday and Thursday, and I'm going to do the same for this week to try and break it up a little bit for you guys. So before we get into it, I want to go over the wrap up from week 14's module. So hopefully you've been able to get the readings done for chapters 10 and 11. Again, for chapters 10, you'll only have to read pages 443 through 447 and 451 through 459. And for chapter 11, read pages 483 through 488 and 501 through 507. So you'll also need to participate and complete in discussion 4, which is going to be due April 28th by 11:59 p.m. and complete lab 10, which is also due April 28th by 11:59 p.m. So for this week's module, we're going to be getting into GNS and GPS, and so you'll be needing to read Volstad Chapter 5. We'll also need to be participating in complete discussion 5, which is due by May 5th at 11:59 p.m. And as a courtesy, please try to get your submissions in earlier rather than later to allow students to reply to your submissions if they choose to for this week. We'll also be working on and completing Lab 11. So this is a quasi GPS lab. You'll see that we will be using Google Earth to collect waypoints for this week's lab activity. So at the top of that lab activity, I give a little disclaimer to make sure that if you do go outside to collect these waypoints, which is required for the lab, to make sure that you're complying by all of the shelter-in-place order and social distancing requirements, and so you need to make sure that you're going somewhere where you can maintain at least a 6-foot distance between other people, and of course you need to be wearing a proper face mask. If you have any questions about that, you can ask me. I can send you some guidelines and links. Also, if you do not feel comfortable participating in this lab by going and collecting waypoints outside, please contact me as soon as possible, and we could come up with an alternative for you. Okay, so you'll also see that we have a reading quiz this week for the Volstad chapters 10 and 11. Again, it'll just be covering those pages that I mentioned above. It's going to open on April 30th at 6:05 p.m., which is this coming Thursday, and it'll be open through next Tuesday, May 5th at 11:59 p.m. Okay, so just for a quick review, what is geodesy? Geodesy is a branch of applied mathematics. It is the science of measuring and representing the size and shape of the Earth, the exact position of points on Earth, and the study of Earth's gravitational and magnetic fields as they change over time. Geodesy is the foundation, quite literally, upon which all other geospatial science stands. Geodesists basically assign addresses to all points all over the Earth. If you were to stick pins in a model of the Earth and then give each of those pins an address, then you would be doing what a geodesist does. By looking at the height, angles, and distances between these locations, geodesists create a spatial reference system that everyone can use. So this is the basis of what our global navigation satellite systems and GPS are based off of. So we have our GNSS, which is a global navigation satellite system, satellite-based technologies that give precise positional information day or night in most weather and terrain conditions. GNSS is the generic term for worldwide radio navigation systems using satellites to provide geographic positioning. The United States government established the first GNSS in 1994 called the Navigation System with Time and Ranging, or NavStar, Global Positioning System. It is a satellite-based radio navigation system that is operated by the United States Air Force. This global navigation satellite system provides geolocation and time information to a GPS receiver anywhere on or near the Earth where there is an obstructed line of sight to 4 or more GPS satellites. Obstacles such as mountains and buildings block the relatively weak GPS signals. So I want you to pause the video here to watch the short video on global positioning systems located on the Week 15 lecture part 1 page on Canvas. It should be located right underneath this video. Welcome back. I hope you enjoyed that short video. Obviously, that video focused more on the ways that the military uses GPS, because our current global positioning system is managed and owned by the U.S. Air Force. But as you'll learn in this class and in hopefully your future GIS courses, there is a huge range of how GPS and GIS are used and what they're good for. Okay, so NavStar is now known more commonly just as a global positioning system, or GPS, and it's comprised of 3 segments. We have the space segment, the control segment, and the user segment. The space segment initially consisted of a core constellation of 24 GPS satellites. Arranged into 6 equally spaced orbital planes surrounding Earth and positioned approximately 20,200 kilometers above Earth's surface, each satellite makes 2 revolutions around Earth in a day. Initially, up to 4 satellites occupied each orbital plane for a total of 24 core satellites in the system. Since then, the number of core satellites has increased to 27. Also, there are some spare satellites used to maintain coverage when servicing core satellites or when they become decommissioned. Though not considered part of the core satellite constellation, additional satellites increase GPS performance. As of June 24, 2015, www.gps.gov reported 31 operational satellites in orbit, with 3 more to launch in 2016. The control segment is made up of a master control station, monitoring stations, and antennas located around the world. Monitoring stations track GPS satellites, ground antennas transmit and receive signals to and from satellites, and the master control station utilizes this information to ensure the health and accuracy of the GPS constellation. Any devices, such as GPS receivers or applications that use GPS technology, make up the user segment. There are many types of GPS receivers, ranging from less than $100 to $1,000. And as you know, we even have GPS receivers within our phones, and we'll be using them in the lab this week to collect waypoints through the Google Earth app. The term recreation grade refers to low-cost receivers. These types of units are suitable for automobile navigation and outdoor recreational activities such as geocaching, a kind of treasure hunt used using geographic coordinates. They're cheap, quick, they have fairly good accuracy, 5 to 15 meters, and they're corrected to up to 2 to 5 meters. Most of them don't feature data collection capabilities, but a lot of apps now do. And even the free apps will do that as well. There is less storage though, and some of the WAS is enabled, and we'll get into WAS on Thursday's lecture. So mapping grade GPS units are ideal for the collection of geospatial data and can offer up to 1 meter of accuracy. These units are capable of recording features such as waypoints, track lines, and polygons. These features can be downloaded to a computer and used with GIS software. Survey-grade GPS units can cost thousands of dollars, but are capable of accuracy within a centimeter. A survey-grade GPS units are suitable for engineering and construction applications. So as we could see with our quick list here, the mapping and survey grade receivers, they're more expensive, but they're still very quick. They have much better accuracy, 2 to 10 meters and 0.5 to 5 meters corrected. And some of those survey grade receivers are going to give you accuracy within a few centimeters, which is very impressive. So with the mapping grade, you do have that attribute storage collection, and so it can range from just tracking those waypoints to allowing you to upload a whole attribute table that you're filling in as you're collecting waypoints. And then you'll have a lot more storage space, and it's not going to be competing with anything else, like if you were to use your phone or just like a TomTom navigational GPS for your car or something like that. And all of the WAS will be enabled. Okay, so before we wrap up, I just want to revisit this first slide and what to expect for this week's module. I forgot to mention a couple of things about Lab 11. Okay, so you will see that it is due May 12th. That means that you have 2 weeks to work on it. And I will not be assigning a new lab for next week. This is the last lab that is going to be assigned for the course. And so I'm doing that to allow you to make sure that you have enough time to get out and collect your waypoints and to acquire any online data that you're going to be needing for this lab, but also to allow you to have time to review and study for the final exam. So next week, and I'll be sending out more information to talk about more about the schedule, and I have a couple of changes as far as when the final exam will be administered. But I will make sure to get all those updates to you at the beginning of next week on Tuesday for the week 16 module, and I'll be sending messages out to everybody individually to explain those changes as well. Okay, thanks for watching. So this will wrap up the part 1 lecture. Please check back in on Thursday, which is April 30th at 6:05 p.m., which is the beginning of class, for the second part of the lecture. And also just a quick reminder that the reading quiz for chapters 10 and 11 will also open at 6:05 p.m. on Thursday, April 30th for you to be able to take.